Hello everyone, this is our refrigeration presentation. My name is Kirsten and I worked alongside Henry and James. The figure on the right shows the physical system utilized in this lab. However, the points of interest were the heat exchanger, the vortex tube, and the refrigeration load. The heat exchanger is intended to bring the temperature back to ambient temperature. Here we assume the tube diameter is constant, there is negligible change in height, and we can ignore the major and minor losses. The heat rate is given by the equation circled in red. The next section of interest is the vortex tube. The vortex tube divides the flow into hot and cold air streams. We characterize it as a function of input pressure, P3. The load is a stand-in for the object or device that we are trying to cool. Here we have an aluminum block that is surrounded by styrofoam. We assume that all heat into the air came from the block. The effective thermal resistance, which is equal to Ka over L, can be found using the equation circled in blue. The objectives of this lab are to model and characterize the heat exchanger, the vortex tube, and the load. In regards to the vortex tube, we want to determine both the hot and cold output temperatures and the hot and cold output mass flow rates in terms of the input pressure. With this information, we can then determine the mass of the load and the thermal resistance of the insulation.
After deploying the LabVIEW VI, make sure that the correct thermocouples needed for vortex tube analysis are connected. These thermocouples measure temperature of the hot air coming from the vortex tube, cold air leaving the vortex tube, and the temperature of the air leaving the load. Also, volume flow sensors are needed to measure the flow of cold and hot air from the vortex tube. Collect data starting from 20 psi to 70 psi in increments of 10 by opening the air supply valve and running the VI. Continue data collection until steady state is reached. The method for the low temperature analysis is very similar to the vortex tube analysis. In this case, however, replace the cold air thermocouple from the vortex tube with the thermocouple for the load mass. Also, the load must be allowed to reheat to ambient temperature at the start of every data collection. For the low temperature, only collect data for 50 and 80 psi pressures until steady state.
First, we will discuss our findings from the experiment focusing on the vortex tube. Shown here are screenshots of the data that was collected for each of the various input pressures. The blue lines represent T3, the green lines are the temperatures at the hot output, and the black lines are the temperatures at the cold output. The red vertical lines indicate where the steady state regions were selected to begin. For every plot besides the 20 psi input, the values seem to reach steady state. However, running the experiments longer would increase the accuracy of this assumption. Shown here are the resulting steady-state values that were obtained from the previous plots. One thing to note is that the cold output temperatures decrease with increasing pressure, and a higher psi value causes more energy to be transferred to the hot and cold outputs. Shown here are plots of the natural log of the hot and cold output temperatures versus the natural log of the input pressure, P3. The temperature difference is approximately the same, but with opposite signs. Here are plots of the natural log of the hot and cold mass flow rates versus the natural log of the input pressure, P3. The slopes of these graphs are similar, as V dot does not depend on temperature. Now we will discuss our findings from the experiment focusing on the refrigeration load.
The calculated experimental values for the insulation resistance are far off from the expected value. This suggests that the assumptions made are not valid, and the lack of calibration causes an initial amount of error to be already present in the system. The time constant and B values calculated from the York regression method are close to the experimental values. Similarly, their uncertainties are not very large neither. It is worth noting that a better fit could possibly be done if this 50 psi run was allowed to go on longer in order to reach true steady state.
The values for tau and B based on the York regression method using the natural log are shown, with small uncertainties. Comparing the system cooling equation to the experimental data, the equation appears to be a good thermal model of the system in the cooling range for the 80 psi input.
Error from the mass calculation indicates that at higher pressures, The assumption that all heat transfer from the load is solely to the air is not as applicable. Considering that the top face of the load is exposed during lab with no insulation, noticeable heat transfer can occur here.
For the relationship between output conditions and input pressure, the results can be stated with confidence using the calculated uncertainty values. Because the temperature is known to a small level of uncertainty based on a single sensor, the system cooling equations can be found with a high level of confidence as well. However, the effective resistance and mass involve uncertainties of several different sensors. Because of this, large levels of uncertainty exist within the models. In addition, the assumptions provided create a poor model of thermal transfer, as can be seen in the difference between theoretical and experimental thermal resistance, likely due to the exposure of one side of the block to atmosphere. In addition, sensors were not calibrated at the beginning of the lab, which leaves the possibility of drift within the sensors.